Okay, I want to give you a few more opportunities here to look at some more examples of work mathematically. We'll also talk about a situation where maybe work could be shown in a way that could get you to a multiple choice question on the AP exam. So, first example here is a work done on a crate. And so you can read it with me. A person pulls a 50 kilogram crate 40 meters along a horizontal floor by a constant force of 100 newtons. This force is it's like on a string, like in the first video, acts at a 37-degree angle. The floor is rough and exerts a frictional force of 50 newtons. We want to know the work done by each force acting on the crate and the net work being done on the crate. So, first off, the work being done by each force. The first thing you want to look at is that we're on a flat surface, right? Plus our object displacement is going this way. If that's the case, obviously our normal force and weight or gravity are not doing any work, because remember, work has to be parallel. Not parallel, perpendicular, no work done. So instantly these two disappear. Normal force and gravity do not do any work on the crate. So now we have to look at the two forces, the applied force or the pulling force and the force of friction. So we'll look at the first one. I'm going to call it the applied force, but the pulling force, right? The work of the pulling is equal to force times displacement times the cosine of theta. So our force in pulling is 100. Our displacement, we said, is 40. And then our angle, cosine of 37. We punch those numbers in and we get 3,200 joules. So 3,200 joules of work is being done by pulling the force. And again, we're only the x component of the pulling force is going parallel with our displacement. So that's the only thing that's doing it. Not all of our 100 newtons of pulling force are pulling this thing. So now let's look at the work of friction. Again, force, displacement, cosine of theta. Now, if you look, these are parallel. Okay, so our angle from displacement to our frictional force is 180 degrees. So our force is 50. Our displacement is still 40. But now we're talking about the cosine of 180 degrees. Now, why that's important is by saying the cosine is 180 degrees, we're actually going to get a negative number. So when we do the math, we get friction doing work of negative 2,000 joules, which we expect to see. So those are our two work done by each crate. Now, to find the net work, all we have to do for part B to find the net work is we take 3,200 and we subtract 2,000 from it, and we get 1,200 joules of net work being done on our box. Okay, another example. We got a hiker that's going up a hill. This hill looks like a ramp, but we're going to call it a hill. Carrying a 15 kilogram backpack to a height of 10 meters. Okay, so we want to find the work to do that, the work done by gravity, and then the net work done on the backpack. And here's what we're going to do, because we want to make this simple. We're going to say we're moving at a constant velocity, which means zero acceleration. Anytime you see that on a problem, right away you're thinking my forces are equal. Okay, so with my forces being balanced, that's a good thing. So here we go. So first off, we want to look at the guy in the backpack. He is displacing himself upward, which means we want to think about the gravity, right, is lifting this thing upward. So we want to think about lifting the pack straight up. So when we do the math here, and since we know we're walking straight up, the angle is irrelevant here. Okay, we're taking the backpack from point 0 to point 10 meters up. The path we take is irrelevant. We're gaining height. So that's what we're talking about. So we're taking the backpack from 0 height to 10 meters. So when we look at A and look at the actual work involved, force d cosine of theta, since displacement and force are both going in the same direction, our angle is going to be 0. So work is going to be the force of lifting the backpack times the distance, displacement's 10. Cosine theta, the cosine of 0 is 1. So really, work is going to be force times displacement. Now that we have that, what is our force? Well, our force is lifting this backpack up. And since the thing that's holding us down is gravity, force of the backpack is going to be mass times g. So our mass is 15, g is 9.8. I punch those numbers in, and I get 147 newtons. That becomes my force. So the force I'm applying is 147 newtons, and my displacement is 10, which means the work being done, okay, by the hiker is 1,470 joules. All right. So now the question is, what's the work done by gravity on the backpack? Well, we're applying a force of 1,470 to lift it up. Gravity's pulling it down. Since we're moving at a constant velocity, the force we're applying to lift it and the force of gravity should be balanced, which means if this is positive 1,470, then for answer for B, it should be negative 1,470 joules. That is the work that gravity's doing. Then lastly, net work. I take 1,470 minus 1,470. What do I get? 0. I get 0 joules of net work being done. If you're moving at a constant velocity, and the two are constant, right? Or the two are counteracting each other, it's going to be 0 joules of net work. So you're not doing any net work because gravity's pulling it down as you're lifting it up. Kind of sad, huh? All that work to lift something just to know that gravity makes it look like you have no net work being done. Lastly, and this is more of a hypothetical question, but something to think about. Does the Earth do work on the Moon? So the Moon, in its rotation around the Earth, wants to go at a tangent, but gravity holds it in. Okay? So it's moving this way. It's displacing that way. But the force is going this way. When we look at this, we see that it is perpendicular. If our force and displacement are perpendicular, what does that mean? We're doing positive work, negative work, or no work. Hopefully, you didn't have to think very long about this. The answer is C. We are doing no work on the Moon, or the Earth's doing no work on the Moon because of the perpendicular nature of the force to the displacement.